Okay, so I have timed myself for 20 minutes, so hopefully I should get everybody out in time for coffee. Yeah, I know. Okay, so I've been working on detecting problems with Erlang message passing errors, so for an intermediate representation of Erlang. So let's start with the problem. It's quite a weak problem. So in this simple Erlang program, we have a client and a server, and the client is going to send a single message to the server. And in this case, we're going to send the atom some stuff, but as you can see, the receive here is only looking for a tuple where the second element is a number. So obviously, we can't send it an atom. This is just going to sit in the mailbox forever. The server's going to leave these messages going to sit in the mailbox. They're not going to get picked up. But on the other hand, like there's also this opposite problem that the receive clause is never getting used. You're sending a message that never gets picked up, and you're trying to receive a message that is never sent. And I think this is a bit like unused variables in your programs. So for example, on line 5 here, we have this name2 variable that's assigned, but never used. And of course, if we put this through the Erlang compiler, we do get a warning. It's a sign of code smell. It doesn't necessarily affect the behavior, but there is something going on here that's unused, and this is suspect. We can't necessarily assign blame, but there is something a bit strange going on. So the problem here really is miscommunication. So then I'm going to have a quick look at trying to gain some understanding about what messages can get sent and which get received. We're going to think about the types of messages that processes can receive. We're going to define a subtyping relation over a part of Erlang's types, over Erlang terms. And then we're going to infer some types for these sends and receives. We're actually going to use this type system. And then I actually wrote a little tool, I wrote an artifact for this that demonstrates some of this algorithm. And then we're going to talk about how we go with this in the future. So let's say that message compatibility is the capability of a message being received. So if I send a message, can you possibly pick it up? And likewise, a message is compatible with a process if the message is compatible with any receive expression in it. So you can have a message compatible with a receive expression if it can pick it up, and you can sort of extend this naturally to a process. But how do we know whether a message is compatible? We need something a bit more concrete. So let's look at some examples. So if we have this receive expression on the left with 3 clauses, we have some guards here. So we have receiving variable A, when A is an atom, tuples, and also like the negation of a type check. So in the first example, we can think of the messages that this can pick up. And we can see that it will pick up this first message, which is atom. So we can see that guard provide us with some type information. This guard asserts that A must be an atom. It's not just free. If we look at the second clause, we get a bit more information. We can see that in this situation we're matching a tuple where the first element is an atom, and we can see that patterns can provide us with some compound type information. For example, we can tell whether things are tuples or lists or binaries or things like that. And at the same time, if it's a free variable in the pattern, then it will bind to anything. It will pick up any value in there if there's no type information about it in the guard. And then also we can have negations, so that will pick up anything that is not an atom. And the thing we notice is that although none of these matched all of the messages, together they will match any message, because if you see here, the third clause is the negation of the first clause, so it's a tautology, so it'll pick up any message. So we must consider all clauses together. So let's actually use Erlang's type system, because Erlang has a dynamic type system, but let's just add a bit of the system. So we have the any type at the top, then we have atoms, booleans, and so on underneath this, where you can either have tuples of an unknown size, or you can have tuples with specific numbers of elements. So you can say a tuple with 2 elements, or 3 elements, or 100 elements. We're also going to introduce singletons. Singletons, you see them as like, if you have a type declaration, you might just see like an atom in quotes, it might be hello or okay or something. We're going to introduce singletons, where we're going to say that, we've got a subtyping relation here, we're going to say that you can have a singleton be a subtype of any other type, as long as you have a value that is that type, and also the values type is a subtype of the type we're checking. So for example, this here we're saying we have an Erlang value L, that type has type S, and we can use an Erlang function to determine the type of L. It's actually quite easy to write. And likewise, a singleton is a subtype of another singleton, so like the atom hello is a subtype of the atom hello, because atom is a subtype of atom, and also we check that they're equal according to Erlang's idea of exact equality here. We're going to introduce subtyping across tuples. So one tuple is a subtype of another tuple, as long as they are the same size, and element-wise, they're all subtypes. And finally, this subtyping relation, which is an extension of this, and the two things on the left, we're going to say it's reflexive, so atom is a subtype of atom, and also, for example, we're going to have transitivity, so Boolean is a subtype of atom, and atom is a subtype of any, so therefore Boolean is a subtype of any. So here we have an example where we have the singleton true, which is a Boolean, which is a subtype of Boolean, because we can instead sort of like give a concrete value to a type via that typing relation. And Boolean is also a subtype of atom, so naturally the entire thing is a subtype of any. And for tuples, we say that we compare element-wise, so true Boolean is a subtype of atom, and integer is a subtype of any, so therefore one tuple is a subtype of another. So that's the preliminaries of a subtyping system for Erlang. This has been done before, and I'm just showing it to you here. So then if we move on, we can actually use this typing relation to define message compatibility. So if there's a message of type S, it's compatible with the receive expression if the receive expression, which has some type of C which will determine in the future, such that S is a subtype of T. So is this like a subset of the values that this receive expression will match? And again, we can extend this to the idea of a process. So a message S is compatible with a process T, with a process if there's a receive expression somewhere in the other process in its past or future that has a type T, such that S is a subtype of T. So we're revolving around this subtyping relation. So let's try and intuitively assign some types to this receive expression we saw earlier. So the first one, it looks like it accepts atom, because the guard tells us that it's only accepting atoms. So you think that the first clause here will accept anything of the type atom. The second one, the first element must be an atom because the guard tells us. However, Y here is free, so it will accept anything for the second element. And we get a tuple of the two things there. And for the third one, it accepts all except atoms. And together, you can get atom or atom any, or all except atom. Or, a bit more formally, we'll introduce some logical connectives here. We can use ors and negations there. But I haven't introduced these to you yet, and they come from the world of flow typing, where you can assign types things based on control flow programs. So we're going to have union types, which if you've ever written a type in Erlang, you see as a pipe. In type declarations, you use the vertical bar. We can have intersection, where in intersection you say it must be both type S and T. So if something, for example, is an atom and a Boolean, it's probably going to be a Boolean, it must be both things at the same time. And we're also going to introduce negation, so we can say all except atom or all except number, or all except any. So the opposite of any is none, but we're going to use an alias. That's just an alias for not any. And usually this subtyping algorithm, once we introduce these types, is incomplete. But there's some related work I'm using from 2013, which actually gives you an algorithm which is both sound and complete with respect to a set theoretical interpretation of the types, which is very useful. So now we've got a fragment of Erlang's type system. We've got some representative types. For example, we have compound types via tuples. We have integers as a subtype of number, and we have booleans as a subtype of atom. So we have sort of distinct types and subtypes in there. So we've got like this representation of Erlang's types. We have some anecdotal observations about message compatibility. We've looked at some clauses and we think these look like they should have these types. I've extended Erlang's type system a little bit with intersection and negation types. We already have union types in Erlang. And I've sort of meshed these together from here on. I've sort of combined the union, intersection, and negation types with that subtyping relation I quickly showed you. The details aren't really important. The inference is the interesting bit. So this is the point where, in my work, I switched from working in Erlang to core Erlang, which is an intermediate representation for Erlang. It's part of the tool chain. And technically, you could say it allows you to target Erlang as well. We remove some syntactic sugar. So you can have commas and semicolons in guards in Erlang, but in core Erlang, these are desugared to calls. And likewise, and also in or else, which are the sort of short-circuiting operators in Erlang, they're represented via case expressions in core Erlang, because core Erlang doesn't have these operators. Guards, in the core Erlang specification, guards must be side effect free, which is of course true of Erlang, but we have this in the specification. So it means that semantically, because there aren't side effects, that a and also and also an or else are semantically equivalent in type information they give us, and we only have certain functions. You can't have user-defined functions which might not terminate or might be impure. And the Erlang compiler helpfully performs some simplifications for us. It does some preliminary dead code checking in the compiler, and you also get some pattern and guard normalization. Some things get desugared, and you get some sort of constant propagation done for you, which is quite useful. And also we've got like first-class handling for these ASTs. Once we compile our code to call Erlang, we take Erlang code, compile it to call Erlang. We've written this tool in Erlang, and we have some libraries already part of the OTP distribution that we can use. So let's use, this is what we're going to use for patterns for our type inference. We're going to have variables. So variable names, variables. We're going to have literals, such as number 2, or patterns like hello. We're going to have a tuple of patterns. And we're also going to have this last one, which is a pattern alias, so you can do x equals, and then have a pattern there. And likewise for guards, we're going to simplify it a bit. We're going to have guard true, which always succeeds, guard false, which always fails, like we do in Erlang. We have negation. This is representing like a sort of shorthand for the type tests you see in the Erlang module, like is number, is atom, is list, is tuple, that kind of thing. We have checking for equality. You'll notice that we're not checking for equality in patterns because we can push it into guards. And also we have this single case expression, which is essentially an if-then-else of if the first branch do T, otherwise do the second branch. And this is what the and also and or else get converted to in core Erlang. You get these instead. So quite quickly, we're going to construct a function that infers some types of guards for us. So we're going to work backwards through a clause. We're going to look at a guard and see what does that guard tell us about the types of things that the clause will accept. So the true guard doesn't say anything, it'll allow any type to come through, while as false, no matter what the types are, it's always going to fail. So it's going to say, it doesn't matter what types you have, I'm never going to let anything pass. Negation, what happens is we're going to sort of flip the type of everything we already have. So if you have not true, that becomes false, so it flips everything. And likewise, if you have not is atom, then that becomes the negation of is atom. So what happens is we're mapping across everything we already have in our sorted variable mapping, where these are just represented differently in Erlang. The type test, what we're going to say is if you have is T V, so like is atom V, then that gives us a type assertion that V has type T. It doesn't tell us anything else about any other variables. And when we have equality, we turn it into a singleton. So we'd say, if you have an equality check in the guard that the variable V is equal to the Erlang term L, or the literal L, then we're going to say, well, now the variable V is a singleton type of the type of whatever the literal is, and the literal itself. And the most complex one is this case. So what happens is we have if this returns true. So here we have this. So this is the success case. So assuming that G succeeds, so we say the G thing happened, then we're going to evaluate the true branch. So we say the first thing happened, G returned true, and we're going to evaluate the second thing. Or there's another option when evaluating this, which is G fails, in which case we evaluate the second branch, so we get not the result of G because that failed. We know that any type assertions it's made have failed, so then we're going to evaluate the second branch. So if we look, so just to prove that things are correct, like we're still on the right track, if you have this is number or is Boolean X in Erlang, we expect it to have this type. You can either have a number or a Boolean. So the compiled core Erlang version, this is a bit of a simplification. This is what it gets compiled to in core Erlang. This is the representation of the lazy or else. What happens is we get this from the previous slide. So we've either got the success case, so it either is a number, in which case we short circuit to true, or in the opposite situation, it is definitely not a number because that first guard failed, and therefore it must also be a Boolean. And because we've got this set theoretic interpretation, we can actually simplify this to number or Boolean, so we get the same type. So we're along the right lines here, which is pretty nice. So we can also do the same thing for patterns. So what we're going to do is, if you've got a variable, we're going to interpret this in a context gamma. We're going to say, assuming we may or may not have some information about the variable, if we do have information about a variable from our guards analysis, then we're going to say, oh, well, the pattern V must be whatever the type we've inferred so far of V is. Otherwise, we don't know. So if it says, if you've got a guard that is atom X, and you have the variable X in the pattern, you know, oh, well, X is atom. We worked that out from the guard. But if X does not occur in the guard, we go, well, it could be anything, because in core Erlang, it's unbound. Literals in the patterns, we do the same thing. We just assign it singleton type. For patterns, we just curse over the elements. So if you've got a pattern, say variable 1, variable 2, variable 3 as a tuple, then it is a tuple pattern. Well, it's a tuple type of the result of it on the first one, so you do it element-wise across the whole thing. And finally, when you have an alias, you combine it with any type information you have about the alias. That's just saying we infer the type of P, and if we know from the guard that V has some type information, we're also going to combine it. So if you say is atom V, and you get some type information about P, you're going to get the type of P and combine it with is atom. So once we have this, we're going to say we can assign types to an entire clause, because clauses in core Erlang always have a pattern and they always have a guard. The guard can just be, by default, is the atom true. So if you compile an Erlang expression that has clauses into core Erlang and your Erlang wants to have any guards, it's just going to inject the guard true for you, because they're the same essentially. So what's going to happen is for a clause, we're going to look at the type of G, so we're going to get information from the guard, and it's going to give us some type information. It might say, give us information about variables. It might say V is an atom, B is a number, and so on. And then what happens is we're going to get the type of the pattern, and we're going to combine it from that type of information we had with the guard. And what we're going to do is, if we have multiple clauses in a C expression, we're just going to take the union of all of them. So we say, the first one might match, or it might be the second one, or it might be the fourth, all the way up to the end. So we say we're just going to take the union of all of the clause types, because it could match any of them. So let's go back to that example and actually give it some types. So the first one, it works out to be atom. The second one works out to give us this tuple type. I'm not going to expand all these, it takes too long. And the third one, we get the negation of atom, as you would expect. And then when we take the whole thing, we get this divisional type that we saw earlier. So now we've got, this is the definition from earlier. Now that you've seen the subtyping relation and the way we can infer simply some types for guards, patterns, and therefore clauses, we'll look back at this definition, and we'll go back to the example from the beginning of the presentation where we had these two incompatible messages going on here. So first thing we're going to do is we're going to work out the type of the receive expression. So what happens is we're going to look at the type of the pattern AB in the context of the guard. The guard in the end turns out to just tell us that B is a number. So what we're doing is we're looking at, we get a tuple type of A, it is number B, which gives us any, and also the variable B, we know it's a number from the guard, so we get that type. And then we're going to cheat a little bit here. We're going to use the same pattern inference function from earlier to get a quick type, an over-approximation of the type for the sent message. And what happens is you get singletons here. So you've got sum here becomes the sum here, and the stuff here becomes the stuff there. So you have a tuple type of two elements where you've got a singleton sum of type atom and a singleton stuff of type atom. The singletons have types attached to them because it's actually an optimization in the implementation. Rather than having to recalculate the type all the time, we just tag it when it's first instantiated, and then we can compare it later. So using these two types here, what we'll do is we'll try and apply the subtyping relation. So we have the send type over here. I want to check whether it's a subtype of the receive type. It is not, because although sum here is a subtype of any, the stuff here is not a subtype of number, so the subtyping relation does not hold, so we conclude that the message cannot possibly be received. So what I did at the end of this was I built a tool. If you look at the paper, there's a link to the artifact. It's fairly preliminary. So we have this subtyping relation with these extended types. We have intersection and negation, which you don't typically use in Erlang, but we have in our tool. We don't expose them to the user directly. It's used for internal representations. We have this simple implementation of an inference, type inference algorithm for guards, patterns, and therefore for entire receive expressions. We are combining all the clauses together. We have this sort of formal definition of message compatibility using our subtyping relation, which I showed you earlier. And most importantly, we have the core Erlang APIs. We've got these APIs in the Erlang compiler that we can use to manipulate trees, fold up definitions, expand definitions, and check the types of things. So the tool hasn't got a name yet, unfortunately. I'm trying to come up with a name that has ER on the end, but it's pretty difficult. So what it does is it goes through all of the functions in a module. It only works at the module level at the moment, and it will assign receive types. So as you can see, client has no receives in it, start has no receives in it, so we say that they can't receive anything, whereas any number here comes from that example we saw earlier, so we inferred in this server body here that we've got this type near the any number. So then what happens is it goes and looks for literal send, so it looks to call the Erlang send functions, be they to registered processes or just the bang operator, and we can determine that should be stuff there, so that should be some stuff. So we get that singleton type from earlier. And then what happens is we check the subtyping relation again, as we saw earlier. So after it does this first pass, it does this second pass, and then it does all the subtype checking. And then at the end, it does produce warnings quite quickly to the user that says, send never received in destination. Perhaps it's an orphan message, perhaps it's a message that was never received, and it's on line 12, and it's a warning that some stuff was never received. Some stuff was sent but never received. And that's the basic implementation of the tool so far. So at the moment, we haven't got all of Erlang's types. We've got some sort of examples, representative examples of types. We think it should be fairly easy to extend our type system to represent all of Erlang's types. We have receive dependency. So the thing I didn't think about is, what if you have nested receive expressions? Receiving one message might rely on another message being sent. But it's interesting in Erlang that it doesn't have to happen in order. So perhaps session types are a bit too strong, but this is a bit too weak. Perhaps there's something in the middle. And we don't have much type information or data flow analysis beyond our own work because we've just written this small tool. So perhaps there's the possibility of integrating with other tools in the community to provide us more specific type information for either messages or receive expressions. For example, there's dialyzer, which I'm sure everyone knows, but an interesting recent development is gradualizer by Joseph Svenningsson. That's actually very, very good work. And tests. This is what I want John's help for. It's really hard to write tests for this because we're working off the core Erlang specification and we don't know if that matches the implementation. So we want to generate messages of types, we want to infer types from receive expressions and throw messages at this process and see if our subtyping relation does hold. Is there bugs in our work? Are there bugs in the Erlang implementation, in the thing itself? We don't know. So the conclusion is it's quite easy to extend Erlang's type system. So we've added these Erlang's type system to achieve this. We can use the subtyping relation to check message compatibility quick enough that we can do it basically in the editor. You get really quick feedback about this. The Erlang compiler and dialyzer don't currently do any of this receive checking. There has been previous work on this, but it never made it into dialyzer, which was quite disappointing. Perhaps there's a chance for integration with these tools. And you can also use the subtyping relation to calculate an upper bound on the number of receive clauses in your expression you require to receive a specific message of a specific type, which also allows us to detect dead receive clauses and dead receive expressions in your code. And we also found it was quite easy to write tools in Erlang because of these very extensive and good APIs. Thank you. That is a link to the slides and the paper. Thank you very much.
Questions?
John?
So, in the example you showed us of your tool,
Yes.
in action,
Yes.
then your tool had linked up the send with the corresponding receive. How did that
So,
happen?
so naively, this is a simplification for the purpose of the presentation. In reality, what happens is we're using named processes at the moment. So we're looking for literal uses of the same process name. This is, I think, the room for the most improvement. I know that my supervisor, Simon Thompson, and his colleagues have done previous work on, for example, in Wrangler, they were checking data flow on PID so they could determine. So, for example, it could determine that this server passed into the client referred to the body of the server. So that's not something we want to implement ourselves, but something we want to integrate with. Yes?
So, something that people sometimes do is if you've got a tail recursive server that risks building up messages that are not understood in its mailbox, then maybe every now and then there'll be a receipt that just receives everything.
Yes.
And throws it away.
So you have to be careful in that situation because it feels a bit dirty to have to do this, like do this cleanup yourself. Perhaps you'd want something cleaner, like from an ideological perspective, you want something cleaner. But also I think there's a difficulty in making sure you don't throw away any messages you actually wanted to keep. So how do you know you're not, for example, throwing away new requests when you do that clearing?
Sure. So actually, that code looks kind of weird, right? Because it receives a message, and then it doesn't use it.
Yes.
And I wonder whether your tool could identify that kind of receive, maybe note that messages of this form are not correctly processed by the recipient. So you might want to generate a warning to send over those anyway.
Yes.
I wonder if you've seen any places where, by poor Erlang time, clauses have been reordered or removed from your original source. There are definitely places where, in the compile cycle for Elixir, things that should have been caught as a compiler warning just vanish because the extra hops. And so I wonder if you've seen any cases of that in your work so far. Like the clause above just being removed, optimized out, and you end up getting false warnings.
So core Erlang is actually very good about this, about false warnings, in one direction, which is whenever the core Erlang compiler, for example, I've simplified a lot of stuff so it actually fits on slides. Like the core Erlang guards are very large and unwieldy. There's a lot of variables you never named and dead case expressions and things. But what the Erlang compiler does is it adds an annotation saying this was compiler generated. So then if it, like these things that you never wrote have warnings from the compiler, it suppresses them because it knows it didn't write because of annotations. But I haven't seen anything removed. I haven't seen dead code removed yet. I've had warnings, but I haven't seen it gone away. Yeah?
Can you do right now, or do you plan in the future you can support OTP behavior?
On what behaviors?
OTP behavior, like figuring out whether my tensor or module.
So yeah, in many ways, OTP behaviors are much simpler to analyze than this because there's a lot of idioms that you can use. So for example, if you have your handle cast or handle call functions, that's very explicitly the area in which you're doing your OTP style communication. So you would infer types on the patterns and the guards of those function clauses in the same way you would a receive expression here. And likewise, I think, this is conjecture here, that it's easier in a OTP definition, in an OTP behavior, to determine where messages are being sent. Usually they're being sent to the same definitions in the same module. So I think, yeah, that's a really good avenue for exploration, because usually you have like a catch-all handle info or handle cast or something, which is just chucking away messages so you don't get function clause match errors. And I think that would be a really good area to catch these problems earlier. Yeah? Sorry,
Yeah.
Scott.
So it seems like you sort of infer the type information from the guard. There might be more type information in the clause bodies as well. Are you making use of that just now?
Yeah, so if I go for a typical sort of type unification approach of, like there'll be function application there, I know what the types of arguments will be and so on. Yes, I think out of scope, because I think there are tools in the community that do that quite well already, so dialyzer and gradualizer will be quite good at augmenting it.
But that will also help you refine the type of receive expression.
Yes, it will, yeah, because we'll be able to backtrack.
Right, exactly.
Yeah, this is very preliminary.
That would be pretty cool.
Yeah, that was my same comment. Just wondering, you put in the future work integrating with gradualizer and dialyzer. So would it be as simple as taking PLT information from a dialyzer and adding it to the gamma context? And
apart from representations, I think so.
Mm.
The only slight problem is that it's locked. In my code, everything, when you see these types here, it's actually essentially a data structure that looks like this. It's not a set of constraints. It is represented like this, and we have a sound and complete algorithm which determines this subtyping relation. Whereas dialyzer and gradualizer use a constraint system. They use sort of a stateful constraint system and gradually add constraints until either they hold or they don't. Like there's add all constraints, it might hold or not. So there's a representation problem, but not, I don't think, a fundamental theoretical problem with integration.
Any first question?
Yeah.
So here you seem to be focusing specifically on communication mismatching errors, right?
Yes.
So in the paper, so I agree with the author messages, right?
Mm-hmm.
The ones that you don't process. But I think you also had another error in the paper, which was like branches in the
That clauses.
yeah, that are never taken. According to me, that's not necessarily something you want to flag.
So
Okay, it's not convention, right?
So I have an example. So you can detect dead received clauses.
Can we get?
So there's the comment that you don't necessarily know where all the messages are coming from in your system, and therefore you might leave the clauses even though they're dead.
Yeah.
So in this example, what I could do is, using a bit of an extension, I can actually determine that up to some point m is all the number of clauses you need to match a message, and then everything afterwards is dead. So in this example, once you get to the point that any is a subtype, you've reached all the clauses, but previously you might just be looking at T. So yeah, I think it's an argument about warnings versus errors. I think it might be worth warning. I think it depends on user experience as to if they think it's worth warning or not, because there's the danger of adding too much noise to the tool. Like if it ends up generating hundreds of warnings, people aren't going to use it.
Questions? If not, let's thank the speaker.